Okay, we are at sort of a cool point in dynamics. I think, to me, just about everything else that we're going to talk about this semester is just really just naturally interesting. There's some cool math stuff coming up, some sort of surprising stuff coming up. And then the thing that we're starting today is just really practical, like useful for everything, you know. So we're getting into this new topic. Get out of here. New topic, linkages. And with linkages, it's not too hard to imagine how this could be useful for all sorts of machines and engines and everything. So a linkage is a collection of rigid bodies. Hey, Dan. Connected by joints. This one is, I shouldn't have to tell you how important this one is. Just kidding, I'm just making this up out of thin air. But, this is the idea. You know, you have, and let's say you apply some external load to it. So this is 1, 2, 3 rigid bodies connected by, in this case, all pin joints. Usual pin joints are going to be the most common things that we do. We're doing this all in 2D. We have to do it in 2D for now because we've only talked about rigid bodies in 2D. In 3D, I said rigid bodies get complicated. And let's say that solving a linkage means finding the angular acceleration vectors of each body. So this is the basis for machines, robotics, biomechanics, lots of biomechanics. Biomechanics. What's the difference between a linkage and a structure? Did I bring that up before? I think I did. Yeah, it moves, exactly. A linkage moves in a structure. So if you build a structure and you do a bad job of building it, it becomes a linkage. So here is, I'm going to just start out by giving you a process for calculating linkages, and then we're just going to do some examples. So process for linkages. So first, just number all the members. The people who took statics with me, this is all going to look very familiar. You know, there's a lot of overlap with the way we treat structures. Second, one by one, isolate each member in the linkage. And use Newton's laws. So I'm talking about Newton's second law and the moment equation. if the member has a fixed point, then you're not going to use Newton's second law. That's what we've been doing with rigid bodies. So how many useful equations do you get? Yeah, perfect. If the member has no fixed point, then you're going to do Newton's second law and rotational Newton's second law. So how many useful equations do you get then? 3. Yep, perfect. And now this is kind of editorializing. So once you're done with all these bodies, say you have 8 members, you've gone through all 8 rigid body analyses, you have all those equations that go along with it. In statics, you're done then. You just solved the system of equations. In dynamics, you're not done. You don't have enough equations. So where do the extra equations come from? They come from joint constraints. That's not how you spell that. Constraints. Okay, so what do the joint constraints do? Well, once you've done Newton's laws for every body, you have all this stuff, that uses the reaction forces, external forces on the body, and you have ways, expressions relating that stuff to accelerations of the center of mass and the angular accelerations. But what you haven't done yet is say, okay, these things that are pinned together or whatever kind of joint you have, like, what do you know about if this linkage is moving through space doing whatever, but these 2 points are connected, say, by a pin? What you know is that the acceleration of that point on this member has to equal the acceleration of that point on this member. If that's not true, then those 2 things can fly apart. Okay, so those are the joint constraints. And so those joint constraints say, the motion of the bodies at the joints obey the joint requirements.
Does that come from Newton's second law?
No, it doesn't. It's going to be its own kind of thing. We're just going to say, we're going to come up with expressions for the acceleration of that point according to this body. Like you've done, so obey joint requirements. Okay, so for rigid bodies, a lot of times the questions that I've asked have said, so you always go through calculating the angular acceleration, and if there's no fixed point, also the acceleration of the center of mass. And then a lot of times I ask you another part that's like, okay, what's the acceleration of this point on the body? Okay, and so that's what you're going to do. You're going to come up with that expression for the acceleration of where that joint is according to one of the bodies. You're going to come up with an expression for the acceleration of that point according to the other body, and you're going to set those two equal.
Why does it go off acceleration and not like velocity?
Well, velocity has to be the same too, but remember that when you're talking about kinetics, when you're using Newton's laws, there's no, like, you're not calculating velocities. Anytime we're dealing with velocities, I just have to give you those because you can't calculate those from forces.
So at the joints, the position, velocity, and acceleration all have to be the same.
Right, right.
We just use acceleration.
We just use acceleration because the position and the velocity depend on what happened before. The accelerations are the only thing that happen at this instant. It's sort of it's a complicated thing to, so at a single instant, velocities do not depend on forces or accelerations. Over time they do, because obviously you can get velocities by accelerating accelerations, you know. But at a single instant, the velocities and the positions are their own thing. So since we're just doing instant by instant, those don't matter to us at all. Like, those aren't in our scope of, you know, thinking about stuff. So we're just going to do the acceleration part. But we will see later that, like, in thinking, I mean, when I do these problems, if I give you velocities or angular velocities for these bodies, those have to also obey the joint constraints. And so there's some math that I have to do in making the problems to make sure that those joint constraints aren't violated by the positions and velocities I give you. Okay. But all right, we're still going through these steps. And so this step is we just go through rigid body analysis for each body. And then it says, okay, but that's not going to be enough. And then the last step is, so first, at each pin joint connecting bodies, we're going to require the accelerations of that point on each body to be equal. These accelerations, like, what do they come from? Well, you've done this kind of stuff before. They come from the watermelon equation, and relative motion. Okay, so for example, you know, you might have an equation that says, let's say body 1 has no fixed point, and body 2 has a fixed point, and they're connected by a pin joint. Then we'd get an equation that says, okay, so at the joint that connects the two, to calculate that acceleration based on what body 1 is doing, the acceleration would be the acceleration of the center of mass of 1 plus angular acceleration of 1 crossed with this r vector from 1 plus omega 1 cross quantity omega 1 cross r1. And we would set that equal to the acceleration of that point according to body 2 that has a fixed point. Well, if you have a fixed point, then you're just going to use the watermelon equation. So we got acceleration, angular acceleration of 2 crossed with r2 plus omega 2 cross quantity omega 2 cross r2. Okay, so we get an equation like that. For body 1, we have to use relative motion. That's what this is. This is the acceleration of the center of mass relative to the ground. This is the acceleration of p relative to the center of mass. For the one with a fixed point, you just have to use circular motion. Okay, there's one other kind of joint constraint that we'll sometimes have to do. If the body connects to the ground, but it's not a fixed point, then the acceleration of the body at that point has to obey the joint requirements. Okay, so what's an example of that? So like, for example, if the body, say that the body connects to the ground via a pin and slot joint. Okay, well, so let's say this is the ground. That's not a fixed point because that, this pin can move along that channel, along that slot, okay? But that doesn't mean that this point can do anything it wants. It's restricted by that slot, right? So what does that slot keep, what kind of acceleration does that slot prevent? Yeah, right. It can't move perpendicularly to that slot. It can only move parallel to that slot. And so what we would do is calculate the acceleration of that point according to this body. And then we would say the part of that acceleration that's perpendicular to the slot would set it equal to 0. Okay. I'm just putting that in now to be sort of thorough for when you come back to this. It probably doesn't make a ton of sense right now, but as we go through examples, it'll make sense. Okay. So let's start out. I'm just going to go through examples, and we'll spend at least a couple days doing examples. So we're going to start out with about as simple a linkage as you could have. Let's say that you have a pin joint on the ground that's connected to this body, and then that body is connected by a pin joint to that body. And I'll number these. So let's say that both of the lengths are 1 meter, and both of the masses are 5 kilograms. And at this instant, so at the instant shown, I guess I do have to number them right now. Let's call that body 1 and that body 2. Omega 1, let's say that omega 1 is rotating this way, okay? And omega 2 is rotating this way. So this one is clockwise, this one is counterclockwise. And so basically, like, if you imagine this is like a leg, it's squatting down, you know. And this is really like, this is the kind of, I mean, this is a simple form of the kind of biomechanics calculations that you do. Like, you can imagine using something like this to figure out like what kind of acceleration a muscle produces at a certain instant, you know. Okay, so omega 1 is equal to negative 10 radians per second. And omega 2 is equal to positive 10 radians per second. And notice that that doesn't, so those have to be given. Like I was saying before, you know, we're not calculating anything having to do with velocities. If there are velocities in it, those have to be provided. And then let's say that there's 100 Newton force applied this way. And let's say we want to calculate the angular accelerations and the contact forces. You know, applied between the members. The angles, let's say that's 45 degrees, and this one is 45 degrees. Any questions about the idea of this problem? What's going on? Okay. Well, I already numbered these. So just one by one, we're going to do a rigid body analysis of each of these members. So I'll start with member 1. And we're going to go through just, for each one of these, we're going to go through the steps of rigid bodies. Okay, well, so like I gave you the steps, the process for linkages. There's 3 steps here. That doesn't sound so bad, except that step 2 is for each member. You go into the 6 or 7 steps, you know what I mean, of the rigid body. So this gets sort of time consuming, but okay. Member 1, does it have a fixed point? Yes, and let's label those points too. So this is A, B, I guess that's all we need. So that's fixed at A. And so step 2, we're going to calculate the mass moment of inertia for the body about that point A. I didn't give widths for these. That means we're assuming these are slender rods. So we got 1/12 times the mass of 5 kilograms times the length squared. Do we have to use the parallel axis theorem? Yes, because we're calculating it about A, not about the center. And so that's going to be plus 5 times 0.5 squared. And so you get 1.6 repeating kilogram meter squared. All right. And now free body diagram. There's a weight force at the center of 5 times 9.81, so 49.05. There's a reaction force at the ground. I'll call this RA. It's an unknown force vector because it's a pin joint. There is a contact force applied to member 1 by member 2. So I'm going to write that as the force on 1 by 2. And then what about that 100 Newton force? How are we going to apply that? Is it 100 newtons applied to each of these two members, or one of the two members, or neither of the two members, or what?
You have to just do it on one.
Yeah, you have to just do it on one. And you can, it doesn't tend to get as complicated in dynamics as it did in statics because we never have more than two members, for the most part, connected at a joint if the thing is free to move. But my rule of thumb is I always apply that force to the lowest numbered member at the joint. Okay, it's just a bookkeeping thing. You can apply it to the highest numbered member. You can imagine that it's applied down a millimeter and then and then it's only applied to one or the two members, you know. But the key thing is if you apply it to both of them, you're double counting that force. The effect is making that force twice as big as it should be. So I'm going to put this force on member 1 because that's the lowest numbered member. Okay, so I'm going to put some notes over here. F12 is the force on 1 by 2. And the 100 Newton force is applied to the lowest numbered member. At that joint. Okay, so that's a complete free body diagram. And now we'll go into the table. Rho, force, moment. Remember the about point is here. So first I'll do the force RA. What's the rho vector from the about point to where RA is applied?
0.
0, yep. The force is RAX, RAY. So the cross product is 0. And then the weight force. The rho vector goes from the about point to where the force is applied. So the vector that we're thinking of, this is the rho vector. Okay. So that is going to be 0.5 times cosine and sine of 45. So that's 0.3535, 0.3535. The force is 0, negative 49.05. And so the cross product is negative 17.34. Then force F12. That's 1 times cosine and sine of 45 degrees, the row vector. So that's 0.7071, 0.7071. The force vector is F12x, F12y. So the cross product is 0.7071 F12y minus 0.7071 F12x. Everyone good with that? And then the last one is the 100 Newton force. Since it's at the same point as F12, it has the same row vector. The force is negative 100, 0. So the cross product is positive 70.71. Do we use Newton's second law for this one?
No.
No, so just go straight to moment equation. And that says, yep, question?
Oh, sorry.
Okay.
No.
Negative 17.34 plus 70.71 plus 0.7071 F12y minus 0.7071 F12x is equal to the mass moment of inertia times the angular acceleration of body 1. And I'm going to rearrange this because we're going to end up with this big system of equations. Really, the only way to solve a system as big as what you're going to tend to get on these is reduced row echelon form. So I'm going to rewrite this with all the variables on one side and all the constants on the other. So our first equation says negative 0.7071 F12x plus 0.7071 F12y minus 1.6 repeating times alpha 1 is equal to negative 53.37. Okay, you with me on that? So that's our first equation for our big system of equations. And now we'll go to member 2. And start over again with the steps for a rigid body. Does member 2 have a fixed point? No. And so the about point is the center of mass. Okay. So the moment of inertia of body 2 is 1/12 times the mass times the length squared. Do we need parallel axis theorem for this one? No. So this comes out to be 0.416 repeating kilogram meter squared. Now the free body diagram. There's a weight force down from the center. That's 49.05. There's a contact force that's on body 2 by body 1. So you can write that as F21. But the whole point of this subscript notation is that Newton's third law says if you switch the subscripts, you just switch the signs. Okay, so I'm going to rewrite this, since we already have a variable F12, I'm going to rewrite this as negative F12. Okay, we're trying to keep the smallest number of variables possible for our equations. And then what about that 100 Newton force?
We don't need it.
We don't need it. We already applied that to member 1, so it doesn't go here. Okay, so Newton's third law says F21 has to be equal and opposite to F12. So that's the substitution we're making. Now the table, row, force, moment. I'll start with the weight force. The about point is here. So what's the row vector for the weight force? 0. 0, negative 49.05. So the cross product is 0. And now we'll do it for negative F12. The row vector goes from the about point to the point of interest, or the point where the force is applied. So it's that vector. That's 0.5 times cosine and sine of negative 45 degrees.
Repeat that.
Yeah. So this makes an angle of 45 with the horizontal. Okay. And so if you think of this horizontal, that means that the angle below the horizontal to that vector is, it's 45 degrees. And so this vector is going to be the length from here to here, which is 0.5, times cosine and sine of negative 45. Okay. So this is positive 0.3535, negative 0.3535. The force vector is negative F12x, negative F12y. And so you get negative 0.3535 F12y minus 0.3535 F12x. Do we need Newton's second law for this one?
Yes.
Yep. So Newton's second law says 0, negative 49.05 plus negative f12x negative f12y is equal to the mass of this body times the acceleration of the center of mass. I'm just going to call this, so a2x, a2y. And this acceleration a2 is the acceleration vector of the center of mass of body 2.
Quick question.
Yeah.
In the Foley problems we were doing, you could write both components of your acceleration vector, and one would just end up being 0 instead of like choosing.
Yeah, like you figured out a direction that it was moving. Here, I mean, I suppose you could figure out the circular arc that thing is traveling on and figure out something about acceleration, but it would be really complicated. I mean, start thinking through how to do that, and so instead we're just going to say the acceleration can be anything.
But you could also use that strategy for like a Foley problem, even if you know what direction the acceleration is. You can just leave it generic and then just solve for both components.
It depends what other stuff you know and don't know. I think the way we've set it up is like you had to recognize. I mean, so basically like when we had rolling problems, think of that as a constraint equation that we could have applied at the end, Okay. It's the same as these joint constraints. It's just saying, okay, this thing isn't going to jump, it isn't going to sink. We're just going to assume that it can only move along this one axis. And we'll do that at the end of these problems. Okay, so our second equation, remember we're just working towards this big system of equations, says, all right, it is f12x, just moving everything over to the right side, plus 5a2x is equal to 0. And the third equation says f12y plus 5a2y is equal to negative 49.05. Everyone okay with that? And now we'll go to the moment equation. Dang it, I knew that was going to happen. I really want that out of there, but okay, whatever. Okay, so the moment equation. And of course it crashed. So add up all the moments, which is just negative 0.3535 f12x minus 0.3535 f12y is equal to the mass moment of inertia, 0.416 repeating, times the angular acceleration of body 2. And so our fourth equation says negative 0.3535 f12x minus 0.3535 f12y minus 0.416 repeating alpha 2 is equal to 0. Okay, so we have 4 equations. Now we're done with Newton's laws. How many variables do we have? Well, I happen to know that it's going to be 6, but let's count them up. So 1, 2, 3. And then 4, 5. And then alpha 2 is 6. Okay, so how many constraint equations are we going to need?
2.
Yep. And it always works out this way. So we know we need 2 constraint equations. How many joint constraints are available? It's always going to match up with what you need. The only joint constraints we have available are saying that the x and y components of acceleration of this point have to match when you calculate it according to this member and according to this member. Okay, so we have an x and a y equation coming to give us our 2 extra equations. You always are going to get the same, like something went wrong if you don't have the same number of constraint equations available that you need after you finish Newton's laws. Okay. Yes?
So in 2D, the maximum possible constraint equations are 2.
No, because you can have multiple, like if you had 50 joints connected by 49 pin joints, then each one of those pin joints is going to have 2. So you'd need 96 constraint equations. Okay? And that's the most I would ever give you on a test, is 96.
Oh.
So,
Around 98.
right, I'd never go 97 or 98. Some people might, but I don't think that's reasonable. Okay. Well, yeah, but you have to do the other problems too. There's 5 other problems. All right, well, we can't do the constraint equations today, but that's what we'll get to next time. If you're interested and you have extra time, I'm not sure if I have any homework problems that I can give you without having done this yet, but see if you can think your way through those constraint equations, and we'll do it next time. Okay, that's all.